Okay. I will share my screen. Okay, can I get your response whether you can see my screen or not?
Can, Doctor, can.
Can,
Okay,
Doctor.
okay, thank you for the response. Okay, so today we will start learning about chapter 2, about the noise. So this is basically the electrical noise that disturbs the communication systems. Okay, so if you remember my favorite picture, so I always mention that this is going to be my favorite picture to all the students. So my favorite picture consists of the transmitter. Okay, so we have the transmitter, okay, connected to the antenna, and then we have the medium or channel. Okay, and then we have the receiver part. Okay, okay. So the noise basically can be generated within the system. Okay, within the transmitter, there will be the noise. Okay, also within the receiver itself, there gonna be noise. Okay, and also within the medium, there gonna be noise. Okay, so the noise are the electrical noise that disturbs the signal transmitted from from the transmitter to the receiver. So basically, the noise will degrade the quality of the transmitted signal. So our objective, our aims is actually to reduce the noise or to eliminate the noise from the system. Okay, so that we can have a high quality of signal transmission. Okay, so ideally we don't want the noise. Ideally, we don't want the noise, but the noise will always happen. Okay, it will always happen in the system, in the ecosystem of the transmitted signal. So we need to reduce it as minimum as possible. Okay, and I will explain to you about this topic. This chapter basically consists of 7 topics. Okay, the first one is the type of noise, and then noise spectral density, and then signal to noise ratio. So this is what we always refer as SNR. Okay, signal to noise ratio. So SNR basically is a parameter that uh, describe the quality of the transmitted signal. Okay, it describes how strong the transmitted signal compared to the noise. Okay, and then noise factor and noise figure. Okay, so noise factor F parameter, noise figure is NF. Okay, noise figure. And then the Friis formula. So basically the Friis formula is used to calculate the noise factor. Okay, and then we have the equivalent noise temperature, and then noise measurement. Okay, so um, for the test, okay, for the test, the topic that will include, I can say that um, all of this will be included in the test. Okay, so test would be in week 7 on Sunday. Sunday, I think Sunday night, if I'm not mistaken. So you can also refer to the group information in the WhatsApp group. I already mentioned the date of the test. Okay. So this is the family of noise. Okay, the noise family. You can see from here we can classify the noise into a few categories. Okay, The first one is what we call as the correlated noise. Okay, and then we have uncorrelated noise. And if you see from the correlated noise, we can divide into harmonic distortion and also intermodulation distortion. Okay, and then what? Then if you see from the uncorrelated noise, we can further divide into external noise and also the internal noise. Okay, so external noise are the noise that generated from outside of the transmitter and receiver. Okay, and we can further divide into a few categories. The first one is the atmospheric noise. Okay, due to the atmospheric layer of the earth. Then the extraterrestrial noise, okay, the noise generated from outside of the earth, which can be divided into solar noise due to the sun activities and also the cosmic noise. Then we have the man-made noise. This is what we call as the industrial noise, the noise due to the human activities in the industry. Then we have an impulse noise and also the interference. Okay, so interference also a part of noise, a noise signal that has the same frequency as our transmitted signal. So this is what we call as the interference. Okay, and then we can also refer to the internal noise. Okay, so internal noise would be the main focus in this chapter. Okay, internal noise is the noise that generated within the transmitter and receiver. So we have the short noise, okay, transit time noise, and also the thermal noise. Okay, so the main focus of this chapter would be the thermal noise. Okay, so you will learn a lot about thermal noise, the noise that is due to the thermal variations. Okay, so the temperature uh, will will determine the values of the noise generated within the system. Okay, so if for your information, we have asked these kind of questions before in the previous semester, where we give the student this uh, noise tree family. So we give exactly the same like this. So I remember that we leave blank some of the boxes. We leave blank some of the boxes, and the student needs to fill in what are the noises inside the boxes, inside these family tree boxes. Uh, so it is an easy question, but if you don't remember, you don't know how to answer this question. Okay, we give this picture in the previous semester. We give the same picture as this one. Okay, we leave blank some of the boxes, and the student need to fill in what are the type of noise inside the box. Okay, so we have asked that long time ago. Okay, and if you go through the type of noise, okay, we can see that the noise can be divided into two categories: the correlated noise and also the uncorrelated noise. So the correlated noise is the noise that always exists. Okay, correlated noise is the noise that exists when there is a signal present. So what does it mean? So if you see from here, for correlated noise, if I show you about the transmitter system, for example, okay, so if there is an input, okay, if there is an input signal to the transmitter, then there's gonna be a correlated noise. Okay, so there's gonna be a correlated noise. Okay, only when there's an input signal, then there's gonna be correlated noise. But when there's no input signal, okay, when there's no input signal, to the transmitter. Therefore, there's no correlated noise generated within the transmitter. Okay, so correlated noise only happens when there is an input signal to the system. Okay, while the uncorrelated noise, if you see the uncorrelated noise, is a type of noise that always present at all time, whether there's an input signal or not. Okay, so uncorrelated noise is a type of noise that always exists whenever there's an input signal or there's no input signal at all. Okay, and the uncorrelated noise we can further divide into internal noise and also the external noise. Okay, so if we go through the external noise, okay, the external noise is a noise that generated outside of the device or circuit. So there are three primary sources: the atmospheric, the extraterrestrial, and man-made noise. Okay, so atmospheric noise is the naturally occurring electrical disturbance originate within the Earth atmosphere. Okay, and it is called as the static electricity. Okay, so this kind of noise is insignificant for signal for transmitted signal above 30 megahertz. So that means it is significant for signal with low frequency, lower than 30 megahertz. Then we can see the extraterrestrial noise, the noise that generated from outside of the Earth. Okay, so we can further divide into solar noise. Okay, solar noise is the noise due to the sun activities. Okay, so we have the quiet condition and also the sporadic disturbance. Okay, then we also have the cosmic noise. Okay, it is a continuously distributed throughout the galaxy. It is a small type of noise intensity because the source of galactic noise are located much further away from the sun. So it is called as a black body noise. Okay, the cosmic noise is a very small amplitude of noise for the cosmic noise. Then we have a man-made noise due to the human activities in the industry. Okay, so the source of the man-made noise mainly due to the spark-producing mechanism, such as the commutators in the electric motors, automobile ignition, and etc. Okay, so we always refer this man-made noise as the industrial noise. Okay, then we have an impulse noise. Is a high amplitude peak of short duration in the total noise spectrum. Okay, so it produced from the electromechanical switches, electric motors, and etc. And finally, we have interference. Okay, interference is external noise. It is from a signal that has the same frequency as our transmitted signal. Okay, so if I transmit signal at 1 megahertz, for example, and you also transmit signal at 1 megahertz, so you are the interference to my signal. Okay, so this is similar analogy if we make an analogy in our classroom, for example. In a classroom, if I speak during my lecture and you also speak with your friends, so that one is also an interference, okay, which will disturb the transmitted signal from my voice. Okay, so interference basically a type of noise that has the same frequency as our transmitted signal. So it will interfere with our transmitted signal, and what happens is that the receiver will be unable to differentiate whether this is my signal or your signal. Okay, so we need to avoid the interference. Then if we go through the internal noise, okay, the first one, the internal noise is a noise that generated within the device or circuit. Okay, as we have seen before, it is consists of three categories: the short noise, transit time noise, and thermal noise. Okay, So the short noise caused by the random arrival of carriers, basically the hole in electron at the output element of the electronic device, such as diode, field effect transistor, or bipolar transistor. Okay, so the short noise randomly varying and superimposed into any signal present. When amplified, the short noise sounds similar to a metal pellets falling on a tin roof. Okay, so it is called as a transistor noise. Okay, so basically this is due to the movement of hole and electron within the transistor. So we call it as a transistor noise. Okay, so if you see that we can see that all of the electronic equipments are made from the transistors. Okay, so transistors consist of the hole and electron that move move within, which will transfer the signal from one point to another point. So that one is what we call as the transistor noise. Then we have a transit time noise, TTN. So this is due to the time taken for a carrier to propagate through the device. So this is what we call as the transit time noise. Okay, so the longer the time taken for the carrier to propagate from the input to the output, the higher would be the transit time noise. Okay, so basically this is due to the delays of the movement of carrier from the input to the output of the electronic equipments, electronic device. So the longer the transit delays, the higher would be the transit time noise. Okay. And then the thermal noise. So this would be our main focus. Okay. So thermal noise is due to the rapid and random movement of electron within a conductor due to thermal agitation and present in all electronic components and communication systems. Okay, so it is often referred as the white noise. Okay, so white noise is a noise that uniformly distributed across the entire electromagnetic spectrum. So white noise doesn't mean that it is a white color. No, white noise means that this kind of noise exists in the entire of frequency spectrum, regardless of what frequency that you use. Okay, if either it is a lower frequency, medium frequency, or high frequency, the noise would be there. Okay, it is not depending on the frequency's value. Okay, it exists in all the frequency spectrum, so that's why we call it as a white noise. Okay, white here is not a color. White here means it is distributed in all the frequency spectrum. Okay, so this thermal noise is temperature dependent, random and continuous, and occurs in all frequencies. Okay, and then there's another parameter what we call as a noise spectral density. Okay, N0. Okay, the parameter N0 is a noise spectral density. Okay, it is a noise power per unit bandwidth. Okay, so that means power divide with the bandwidth. Okay, so you're gonna get the noise spectral density. So the unit of power in watts, and if you divide with the bandwidth of the transmitted or received signal, which is in hertz. Okay, so you're gonna get a value. Okay, you're gonna get a value with the unit of hertz. Sorry, you're gonna get the watt per hertz. The unit gonna be watt per hertz. Okay, or equivalent to watt second or joules. So watt per hertz is actually watt second, or we can mention it as a joules parameter. Okay, so if you see from here, so if the noise is wide, constant with frequency, then the total noise power N in the bandwidth is equal to Bn0. Okay, so that means, okay, so that means if you want to calculate the total noise power is equal to the bandwidth. Okay, the bandwidth multiplied with the noise power spectral density. Okay, so bandwidth normally BW, and then multiplied with N0. So this is the total noise. Okay, and this parameter is very important. It is utilized in the signal to noise ratio calculations. Okay, SNR. Okay, so the thermal noise density can also be written as N0 equal to KT. Okay, where K is a Boltzmann constant in joules per Kelvin, and T is the receiver system noise temperature in Kelvin. Okay, so that means this N0 can be calculated by multiplying the Boltzmann constant with the noise temperature in Kelvin. Okay, so class, remember the temperature parameter in your syllabus would be calculated in terms of Kelvin. So all temperature parameter in your syllabus would be in Kelvin, not in Celsius. Okay, I will show you later about that. Okay, N0 is also commonly used in the link budget as a denominator of the important figure of merits ratio EB over N0 and ES over N0. So what is EB over N0? EB over N0, EB is a energy bit, okay? Is a bit energy divided with the noise spectral density, while ES is a symbol energy per noise spectral density. Okay, so both of these are the important parameters to determine the signal quality, especially in the digital system. Okay, so you're going to see both of these parameters in chapter 4 later. Okay, when we learn about digital system. Okay, so this is the noise power calculations. Okay, so noise power Pn, okay, Pn is actually calculated from uh, from minus B to B of N0 over 2 df, okay, or N0 times B. Okay, so you can also written this as KTB. So from here, N0B, okay, we can describe this as KTB. Okay, and the unit is in terms of watt. Okay, so what is KT? Okay, so before that, so if you see that the noise power, okay, so if you see from the frequency spectrum, from the frequency spectrum, so this is P versus F, power versus F. So if you see that this is our frequency spectrum, okay, this is our frequency spectrum, and this is minus B until B. Okay, so basically we want to calculate the total power from minus B until B. So that's why we use a integral of minus B until B N0 over 2 df. Okay, and we're gonna get N0B. Okay, B is this the total bandwidth. So this parameter is very important. Okay, you can always remember these equations, KTB. Okay, so K is a Boltzmann constant. Okay, it's a constant parameter, 1.38 times 10 power of minus 23 joule per Kelvin. Okay, and the bandwidth here is in terms of hertz. Okay, T is the absolute temperature in Kelvin. Okay, if you see from here, in your lecture notes, the room temperature is written as 17 degrees Celsius or 290 Kelvin. Okay, normally our room temperature in Malaysia, we can say that 25 degrees Celsius. Okay, but if you see from the Wayne Thomas's book, okay, he mentioned that the room temperature would be 17 degrees Celsius by default. Okay, so by default, in your lecture notes, the room temperature would be 17 degrees Celsius or 290 Kelvin. So how do we convert from Celsius to Kelvin? Okay, so in order to convert from Celsius, degrees Celsius to Kelvin, okay, you have to uh, plus, you have a value in Celsius, you need to plus with 273. Okay, then you get a value in terms of Kelvin. Okay, for example, 17 degree Celsius plus 273, you're gonna get 290 Kelvin. Okay, remember, all temperature calculation must be in terms of Kelvin. Okay, so if you see from the KTB, from the KTB parameter, we can say that the noise is highly dependent to the temperature. Okay, the higher the temperature, the higher would be the noise power. Okay, so therefore keeping the electric circuit cool will make the noise level low. So that's why we need to keep our electronic device in a cool environment, so that we can reduce the amount of noise. Okay, so the higher the temperature, the higher would be the noise. So basically, we want to reduce the amount of thermal noise inside the electronic device. Okay, the noise voltage. Okay, so so figure 2.4 shows the equivalent circuit for a thermal noise source. Okay, so we have a thermal noise source from here. Okay, this is the thermal noise source. Okay, which consists of a noise voltage source over here, and we have the internal resistance over here. Okay, and this noise source is connected to the load. Okay, so we have the load resistor over here. Okay, R. Okay, so from this simple equivalent circuit, okay, we want to calculate the noise voltage, and we want to develop the noise voltage equation. Okay, and if you see from here, the internal resistance is connected in series with the RMS noise voltage Vn. Okay, so R internal is connected in series with Vn, and R internal is also connected in series with the R load. Okay, so for the worst condition, okay, the worst conditions means the highest noise. Okay, the highest noise that can occur in the system. So the load resistance would be R equal to the internal resistance. Okay, so if R load equal to R internal, okay, so this is gonna be the worst conditions, the highest noise that we can see from the output. Okay, so the noise voltage will drop across the R load as half of the noise source. So when the load resistance equal to the internal resistance, what happened is that the voltage drop at the load would be half of the noise source voltage Vn. Okay, so if both R are the same, that means the noise voltage at the internal resistance and also the load resistance will be equal, Vn over 2. Okay, so this would cause the voltage drop as at each of the resistance going to be Vn over 2. Okay, so this is going to be the worst conditions. Why is it the worst conditions? And if you see the noise power Pn developed across the load, the resistor is KTB. So we can develop the noise voltage equations from the noise power equations. Okay, so if you see from the equations, Pn equal to KTB. Okay, where this is also equal to V square over R. Okay, remember the power calculations. The power calculation is equal to Vrms square divided with R. Okay, so the RMS voltage at the worst condition, so we use the worst case scenario, the highest voltage drop as possible, which is a Vn over 2. Okay, so we use the highest VRMS, which is during the worst conditions, which is a Vn over 2. So Vn over 2 is a VRMS, the highest VRMS during the worst conditions. And then V over 2 square divided with R. So you're going to get Vn square over 4R. Okay, so Vn square over 4R is equal to KTB. Therefore, Vn square gonna be 4R KTB, and Vn would be square root of 4R KTB. Okay, so this is the final equations for Vn. Okay, square root of 4R KTB. Okay. Okay, so now we go to the example. Before we start answering the example, can I get your response? Are you still there? Can you see my screen?
Ada, boleh doktor.
Okay. Sometimes saya nak dapat respon takut saya cakap sorang-sorang. Okay. Okay. So example 2.2 calculate the thermal noise power available from any resistor at room temperature 290 Kelvin for a bandwidth of 1 megahertz. Okay. So you are given the temperature, you are given the bandwidth B. Okay. Calculate also the corresponding noise voltage. Given R 50 ohm. So the question asks you to find the Pn, how much would be the Pn, and how much would be the Vn. Okay, so thermal noise would be Pn is equal to KEB. Okay, so how much is this? If you see from here, KTB, so that means this is 1.38 times 10 power of minus 23 times T times 290 Kelvin times B. B is a 1 mega. Okay, try use your calculator whether you can get the same answer or not. 1.38 exponent minus 23 multiplied 290 multiplied 1 mega. Sorry, this is 1 mega. 1 mega. Okay. Multiplied with 1 mega. So I get 4 point. Do you get the same answer? Jawapan yang sama tak? Okay, can you get the same answer? Boleh eh? Can I get your response?
Boleh doktor.
Boleh
Okay. Okay, then if you see from the noise voltage, so this is K, square root of 4R KTB. Okay, so this is square root of 4 times R is 50. Okay, KTB, we already know the KTB. Okay, this is yeah, 10 power of minus 15. Okay, we already know the for our KTB. So KTB we already know. Okay, so I just put it over there. Okay, so times 4 times 50. Okay, and then square root of answer. So you're gonna get this 8.947. Okay, times 10 power of minus 7 volt. Okay, so this is easy, straightforward. Okay, and I will go to the next example. Okay, tadi boleh hopefully there's no problem here, and I will move to the next example. So the next example for an electronic device operated at temperature 17 degrees Celsius with a bandwidth of 10 kilohertz. Determine the parameters. Okay, so if you see from here, if you see from 2.3, so whenever you get a parameter in Celsius, you have to change it as soon as possible into Kelvin. Okay, so 17 plus 273. Okay, so you're gonna get 290 Kelvin. Okay, so the first question asks you to find the noise power in watt and also in dBm. Okay, so Pn is equal to KTB. Okay, so this is equal to 1.38 times 10 power of minus 23 times 290 Kelvin times 10 kilo, 10 times 10 power of 3. So this is, so 1.38 exponent minus 23 multiplied 290 multiplied with 10 kilo. So I get this gonna be 4.002 times 10 power of minus 17 watt. Okay, so how can I change it into dBm? So that means Pn in terms of dBm. Okay, so you can write this as 10 log, okay, 10 log of power 4.002 times 10 power of minus 17. You divide with the reference value 1 milli. Okay. And then you're going to get the answer. Okay. So if you divide with 1 milli, and then 10 log of answer, you're going to get this one as well. Down here, minus 133.977977 dBm. Okay. So plus, if my answer is wrong, please correct me. Okay. Okay, so maybe I can check again. 4.002 exponent minus 17. If I divide with the reference value 1 milli, and then 10 log of answer, so I'm gonna get minus 133.977 dBm. Okay. Can you get the same answer? Can you get the same answer? Can I get your response?
Yeah, betul.
Okay. And then what? The next question asks you to find the RMS noise voltage for 100 ohm of internal resistance. So this is RI, and also R, okay, load resistance. Okay. So the thing that we want to calculate here is across the load resistance actually. So what we want to calculate is actually square root of, so this is Bn is equal to 4R KTB. Okay, so this is square root of 4R, 4 times 100 ohm, okay, for the load resistance, multiplied with KTB. So KTB here is 4.002 times 10 power of minus 17. Okay, so 4 times 100 times 4.002 exponent minus 17. Okay, and then you do the square root of answer, and you're gonna get the value 1.2652 times 10 power of minus 7 volt. Okay, so I double check again. 4 times 100 ohm times 4.002 exponent minus 17. Okay, then I do square root of answer, and then I'm gonna get 1.2652 times 10 power of minus 7 ohm. Okay, so this is the RMS noise voltage. Okay, so if you have question, you can ask. Otherwise, I will move to the next example. Okay, so class, you have to double check my answer. If you get different answer, then you have to inform me as soon as possible. Sometimes I wrongly calculated the values. Okay, sometimes I give the wrong answer due to the careless mistake during my calculations. So you have to inform me if your answer is different. Okay. So we go to the next example. Example 2.4, two resistors of 20 kilo ohm and 50 kilo ohm are at room temperature 290 Kelvin. So you see that the room temperature by default in your lecture notes is 290 Kelvin. So we have two resistors, R1 and also R2. Okay. For a bandwidth of 100K kilohertz. Okay, so this is bandwidth. Calculate the thermal noise voltage generated by each resistor. So we want to calculate the noise voltage, the RMS noise voltage. So remember that noise voltage is Vn is equal to square root of 4R KTB. Okay. So for each resistor, we have to calculate the Vn for R1, okay, Vn1 for R1, and also we need to calculate Vn2 for R2. Okay, so this is already been given the answer. Okay, if you see the above calculations, the above calculations for Vn1, for R1, okay, for resistor number one, if we calculate uh, the RMS noise voltage, square root of 4R1 KTB. So square root 4 times 20 kilo ohm of R1 multiplied with Boltzmann constant multiplied with room temperature multiplied with the bandwidth 100 kilohertz. Okay, so you're gonna get 5.66 times 10 power of minus 6 volt. Then for R2, okay, so the RMS noise voltage across R2 can be calculated as square root of 4R2 KTB. So square root of 4 times 50 times 4 times 50 ohm, okay, multiplied with Boltzmann constant, multiplied room temperature, multiplied with the bandwidth. So you're going to get 8.95 times 10 power of minus 6 volt. Okay. So this is for question A. And if you see from here, question B. So question B said, what about if two resistors are connected in series? That means R1 is connected in series with R2. Okay, so this is R1 and R2. Okay, so we need to find out how much would be the Vn across the series of two resistors. Okay, two resistors connected in series. So how much would be the Vn? Okay, so in this case, you have to find out how much would be the total resistance for connected in for resistor connected in series. Okay, so the total resistance for two resistor connected in series is R1 plus R2. Okay, so you're gonna get 70 kilo ohm. Okay, 70 kilo ohm of total resistance connected in series. Okay, then from here you can calculate the total RMS noise voltage. Okay, Vn total. Vn total is equal to square root of 4R KTB. So square root of 4 times R total 70 kilo times Boltzmann constant times room temperature times the bandwidth. So you're going to get 1.06 times 10 power of minus 5 volt. Okay. So this is question number 2. And then if you see question number 3, okay. So question number 3 mentioned that two resistors connected in parallel. Okay. That means we're going to have R1, okay, connected in parallel with R2. Okay, so both of these is connected to the ground. So we have this R1 and we have this R2. Okay, so we have to find the total resistance. Okay, so total resistance, if you see 1 over R total is equal to 1 over R1 plus 1 over R2. and then inverse square. Okay, so if you see from here, you can get this R total. Okay, so R total, if you see from here, 1 over K plus 50K. 7%. So 1.4, 14.28, 14.2857 actually, 14.2857 kilo ohm. Okay, so what I did is actually 1 over R total is equal to 1 over 20 plus 1 over 50. Okay, this is minus 1, and then you're gonna get a value in terms of kilo ohm. Okay, so you get this 14.28 kilo ohm, and then you can put inside the total noise voltage, total RMS noise voltage. So square root of 4 times R total resistance 14.29 kilo ohm multiplied with 1.38 times 10 power minus 3 Boltzmann constant, and then multiply room temperature, and then multiply with the bandwidth. So you will get 4.78 microvolt. Okay, finish. So this is also straightforward. Okay, so if you have question, please ask. Otherwise, I will move to the next slide. Okay, if there's no question, I will move to the next slide, which is about the correlated noise. Okay, so correlated noise is a noise that only present when there is a signal. Okay, so when there's an input signal, then there are going to be correlated noise. Okay, so correlated noise we can divide into two categories: harmonic distortion and also the intermodulation distortion. So harmonic distortion is the unwanted harmonics of a signal. Okay, of a signal. So the keyword here is a signal produced through nonlinear amplifications. Okay, harmonics are integer multiplies of the original signal. So that means for a system, okay, if you have a one input, okay, if you have one input signal, okay, one input signal, then there's gonna be a harmonic distortion. Okay, this is a single input signal into a uh, into a into an electronic device. Okay, so when there's a single input, when there is a one input signal, there will be a harmonic distortion produced by the system. Okay, so harmonic distortion we can divide into a few set of orders of harmonic distortions. We have second order, third order, fourth order, sixth order, and so on. Okay, so you're gonna see later what are the differences: second order, third order, and so on. Okay, so second order harmonic distortion is the ratio of RMS amplitude of the second harmonic to the RMS amplitude of the fundamental. Okay, and then the third order HD is the ratio of RMS amplitude of the third harmonic to the RMS amplitude of the fundamental. So what is this actually? So if you see this for the second order, okay, for the second order HD, so this is actually equal to the amplitude of the second harmonics divide with the RMS amplitude of the fundamental. Fundamental here is V1. Okay, and normally we multiply with 100% to get the value in terms of percentage. Okay, a value in terms of percentage. And for the third order, so I write here. So third order. So I write above here. Third order HD is equal to the RMS voltage of the third order, okay, of the third harmonics, which is V3 divided with the fundamental V1. Then you have to multiply with 100% if you want to get the value in terms of percentage. Okay, similar with the fourth order, fifth order, sixth order, and so on. Okay, you just need to divide with the V1, the fundamental amplitude of the fundamental value of the signal. Okay, then we have the total harmonic distortion, THD. THD is the ratio of the quadratic sum of the RMS values of all the higher harmonics to the RMS value of the fundamental. So how can we calculate the THD? So THD is actually equal to V higher divided with V fundamental. So what is V higher? V higher is actually the quadratic summation. Okay, the quadratic summation of the RMS noise voltage. So you have to make a summation, okay, a summation of V2 square plus V3 square plus V4 square until Vn. So this is actually dot until. So if you see that this is plus and then dot Vn square until Vn square. Okay, and then you do the square root. Okay, and then you do the square root. Then you divide with V1. So it is actually like this. So THD is actually equal to the quadratic summations and then square root. This is V2 square plus V3 square plus until Vn square. Okay, divide with V fundamental, okay, the first amplitude, okay, of the signal, and then you get this value in terms of percentage. Sorry, you have to multiply with 100% first. Multiply with 100% if you want to get a value in terms of percentage. Okay. So this is the harmonic distortion. And if you see from the picture, from the graph over here, you can see graph A. So graph A is about HD, harmonic distortion. Okay, you see that we have a single input signal. Okay, we have a single input signal with frequency of F1, and the amplitude of the fundamental input signal is V1. So the output, okay, the output frequency spectrum gonna be like this. So you have the input, the fundamental, and you have the harmonics located at 2F1, 3F1, and 4F1. So this is example. Okay, we have three harmonics spectrum located at 2 times frequency F1, and then 3 times frequency F1, and then 4 times frequency F1 with amplitude of V2, V3, and V4. Okay, so in this example, if you want to calculate the total harmonic distortion, it's going to be V2 square plus V3 square plus V4 square, and then you do the square root, then you divide with V1, and then you multiply it with 100%, okay, 100%. So you get the total harmonic distortion. And you see, class, the location of the frequency of the harmonic is located at, if you see, the second harmonic is located at frequency 2 times the fundamental frequency F1. The third harmonic is located at 3 times the frequency of F1. The fourth harmonic located at 4 times F1. And then the fifth harmonic located at 5 times F1. So basically the frequency of harmonics, the frequency of harmonic is actually located at n times F1. Okay, so you're gonna get the location of frequency of the harmonics. Okay, and then what? The next part is intermodulation distortion. Okay, so this is also important. Intermodulation distortion. Intermodulation distortion is generation of unwanted sum and different frequency. Okay, generation of unwanted sum and difference frequency. So you see that the word unwanted, we don't want this actually. Unwanted sum and unwanted difference frequency. When two or more signals are amplified in a non-linear device, such as signal amplifier. So you see that here, if I make a mixer like this, we have two input at least. Okay, at least we have two input. Then they're gonna be a intermodulation distortion. Okay, at least two input. Okay, at least two input. Then at least two input you put inside the system. Two input to the system. Okay, then they're gonna be a intermodulation distortion. So the sum and different frequencies are called the cross product. Okay, so class, if you see from the previous graph, okay, so this is actually referred to graph B, okay, where you have two input signal, two input signal F1 and F2 with amplitude of V1 and V2. Both of these signals are put inside a nonlinear device, and what happens is that the output will produce a intermodulation distortion. Okay, so you see that the unwanted sum is located at some frequencies, F1 plus F2. Okay, so this is unwanted sum. And then unwanted difference is actually F1 minus F2, located at F1 minus F2. Okay, with a certain amplitude. So unwanted sum is located at some frequencies, F1 plus F2. Unwanted difference is located at difference frequency, which is F1 minus F2. So these are the unwanted frequencies that actually we don't want both of these. Basically, we don't want both of these. Okay, we want to remove this actually. This is intermodulation distortion. Okay. So the unwanted sum and unwanted difference frequency are called the cross product. Okay. So mathematically, the sum and difference frequencies are calculated as cross product M F1 plus minus and F2, where F1 and F2 are the fundamental frequency and F1 larger than F2. Remember, we don't want negative frequency. There's no such thing as negative frequencies. Okay, so when you want to make, if you want to subtract the frequency, make sure that you produce a positive value. Okay, and then M and N are positive integers between 1 and infinity. Okay, any integer between 1 and infinity. So let's do the example. So the first example here, 2.5, is about the harmonic distortion. Okay, The first example here is about the harmonic distortion. And if you see here, determine the second, third, and 12th harmonics for a 1 kilohertz repetitive wave. Okay, so this is the fundamental frequency F1. Okay, this is the fundamental frequency F1. So if you want to determine how much is the F2, so you have to determine F2 and then determine F3 and then determine F12. How much? Okay, so the answer would be like this. Okay, when you want to determine the second harmonic, the location of second harmonic, okay, you can write like this: 2 times fundamental frequency F1. Okay, so the second harmonic, second order harmonic, is located at 2 times 1 kilo, which is 2 kilohertz. Okay, then the third harmonic is located at 3 times F1, so you get 3 times 1 kilo, so you get 3 kilohertz. And then the 12th harmonic is located at 12 times F1, and you get 12 times 1 kilo, so 12 kilohertz. So these are the locations of the harmonics. Okay, it depends on how many, until how many orders you want to find out. Okay, you can find until 100 if you want. So there are harmonics is a small amplitude of signal spectrum produced through the nonlinear amplifications, nonlinear mixing. So if you see from here, the second question asks you to find the percent of HD. Okay, so second order, find the second order HD. Okay, and then find the third order HD. Okay, for a harmonic distortion for a fundamental frequency with amplitude of, so you are given V1 equal to 8 volt RMS, and then V2 is given as 0.2 volt. V3 is given as 0.1 volt. Okay, so you have to determine second order, third order, and total, and also the THD. THD until third order. Okay, THD until third order. So how to do that? Okay, so the second order harmonic distortion is equal to V2 over V1 times 100%. Okay, 100%. So 0.2 divided with 8 multiplied with 100%, so you get 2.5%. Then the third order is V3 over V1 multiplied with 100%. So this one is 0.1 divided with 8 multiplied with 100%. So you get 1.25. 1.25%. Okay. Then the THD in this example, the first question A and question B is different actually. You might wonder why we are not calculated the 12th harmonic. Okay, because the question only mentioned up to third harmonic. Okay, the question only mentioned up to third harmonic, so therefore we calculate until the third harmonic in this example. Okay, so percent of total harmonic distortion is square root of, okay, square root of V2 square plus V3 square multiplied, and then square root divide with V1. Okay, so V2 square plus V3 square and then square root divide with V1 multiplied with 100%. So you're going to get 2.75%. Okay, 2.795%. Okay, so this is straightforward. Okay, very easy. So if you have question, please ask. Otherwise, I will move to the next slide. Okay, so the next slide is about um, intermodulation distortion. Okay, this example is about intermodulation distortion when you have two input. Okay, so you have two input frequencies. Okay, so this is F1 and this is F2. Okay, calculate the first three harmonics present in the output for each input frequency. So remember, for each input frequency, it will produce harmonics. Okay, so you need to calculate up to third order of harmonics. You have to find out the location of F1, F2, and F3. Okay, so you see that the first for the first input frequency 3 kilohertz. Okay, for the first input frequency 3 kilohertz, you can see that the harmonic, the first one is the fundamental frequency, and then the second harmonic is located at 2 times the fundamental frequency. You get 6 kilohertz. The third harmonic due to the first input frequency. So therefore you get 3 times F1. So you're gonna get 3 times 3, so you get 9 kilohertz. So this is only due to the first frequency signal. And if we move to the second input frequency, 8 kilohertz, okay, remember we have two input. Each input will produce harmonics at the output. Okay, each input signal will produce harmonics at the output. Okay, and for the 8 kilohertz input, you're going to see that the first one is a fundamental frequency. The second one is the second order harmonic located at 2 times original frequency, 2 times 8. So you're going to get 16 kilohertz. Okay, and the third order harmonics located at 3 times 8 kilohertz. So you're going to get 24 kilohertz. Okay, so these are the harmonics produced by the input. So now we know the location of the harmonics produced by the input. Okay. Then, if you see from the second question, okay, the second question asks you to find the cross product. Okay, find the cross product frequencies for a value of M and N, 1 and 2. So we have to find the value of M and N. So find the cross product when M and N is equal to 1 and 2. That means if you see from here, M. So this question is actually a bit confusing. In this example, M can be 1 and also 2. N also can be 1 and 2. So don't be confused in this example. So M and N both can be 1 and 2. Okay, so that means we have to find out the cross product. Remember the cross product. The cross product is actually equal to M F1 plus minus N F2. Okay, this is the cross product. Okay, remember F1 must be larger than F2. Okay, in this case, F1 must be larger than F2. Okay, so therefore, if you see from here, we have to make a table. Okay, so since we have two numbers, two combination numbers. That means we're gonna have four combinations, okay, of four combinations of m and n. So if you see the first row here, m equal to 1, n equal to 1. That means m f1 plus n f2. So 8 plus minus 3. Okay, for the cross product. That means we're going to have 8 minus 3, we're going to get 5 kilo. 8 plus 3, we're going to get 11 kilohertz. Okay. Both of these are the cross product values. Then for m equal to 1, n equal to 2. That means 8 times 1, 8. 3 times 2, we're going to get 6. So therefore, 8 plus minus 6. So you're going to get 2 kilohertz. 2 kilohertz, we get 8 minus 2. And then 8 minus 6. Sorry, 8 minus 6, you're going to get 2. 8 plus 6, you're going to get 14 kilohertz. Okay. And then m equal to 2, n equal to 1. That means 8 times 2, 16. 3 times 1, 3. Okay. So 16 minus 3, you're going to get 13 kilohertz. 16 plus 3, 19 kilohertz. Okay. Then the fourth row, here, m equal to 2, n equal to 2. That means 8 times 2, 16. 3 times 2, 6. So 16 minus 6, you're going to get 10 kilohertz. 16 plus 6, you're going to get 22 kilohertz. So these are the cross products at the output. Okay. These are the cross product at the output. Okay. So that's why when you do the if you draw the frequency spectrum, you're going to get a few sets of different values at 2 kilohertz, at 5 kilohertz, okay, and then at 10 kilohertz, 11 kilohertz, 14 kilohertz, and so on. So there are many harmonics produced at the output. So this is, you can say that this is amplitude versus frequency. Okay, so you get the different values of harmonics at the output. Okay, the input we have only two. We have only two input. Okay, and when it goes through the device, through the electronic device, it produces harmonics at the output. Okay. Okay. So the next topic would be, so class, if you don't have questions, I move to the next topic, okay? Signal to noise ratio. Before we start, can I get your response again? Are you still there? Can you hear my voice? Can you see my screen?
Can, Doctor, can.
Okay. Okay, the next topic is signal to noise ratio, SNR. So this is very important for the test and final exam. Okay, this is very important for the test and final exam. Of course, there are going to be questions about SNR. Okay, so SNR is actually the ratio of signal power, okay, divide with noise power. Okay, so signal power divide with the noise power. So this is actually the parameter that shows the difference in terms of signal and noise. So it shows how big is your signal strength compared to the noise strength. Okay, ideally, ideally, we want the SNR to be as high as possible. Ideally, okay, we want SNR to be higher. Okay, if SNR is higher, that means our signal strength is much stronger than the noise strength. Okay, ideally we want the SNR to be as high as possible. The higher the SNR, the higher would be the quality of our signal. Okay, so ideally we want higher SNR. So if you see from here, if SNR is a ratio of power, that means we're going to get a value without a unit. Okay, P divided with P is a value without a unit. Okay, so for example, 10 watt divide with 2 watt, for example. So you're gonna get 5. No unit. Okay, it's a unitless parameter because this is a ratio. Okay, so for a unitless parameter, we can convert into decibel. So it is 10 log of SNR. Okay, so you get a value and the unit is decibel. Okay, and then if we have a ratio of signal voltage over noise voltage, so what to do actually? So it is actually like this. So initially you see that initially we have power PS divide with PN, right? So this is actually Vs square over R divide, this is RMS in terms of RMS. Class, do you know that power calculation is actually V RMS square divide with R, right? And power also is actually equal to V square over 2R. So this is actually V peak. If we calculate the peak value, so we have to divide with 2R. Okay, so in this case, it doesn't matter you want to use the RMS or you want to use a peak value. Okay, so in this case, this is for example, RMS values. For example, so this is Vn square divided with R. So R can be cancelled. So you're gonna get Vs over Vn square. Okay. So if you do that in terms of decibel, if you change to decibel, that means 10 log Vs over Vn square. So this square can be put in front. Okay. So that's why it becomes 20 log. Okay. So now you know that 20 is not a magic number. Okay. It is actually from the square. Okay. From the power square. So it becomes 20 log. Okay. So let's do the example. Example 2.7 for an amplifier with an output signal power of 10 watt. Output signal power. So this is output signal power. So this is SO, and this is output noise. So this is NO and out. Okay, S out over N out. So what is this actually? So if you have a system like this, okay, and here is the S input, here is the N input, and here is the S output, here is the noise output. Okay, so we are calculating the output part. Okay, the output. How much would be the SNR out? Okay, so here the S over N is equal to signal power, okay, which is 10 watt divide with noise power 0.01, so you get 1000. So in terms of decibel, 10 log 1000, you're gonna get 30 dB. Okay, and plus in the exam, you don't need to write unitless, no need. Okay, it becomes funny if you write like this, unitless. It is enough if you just write 1000. Okay, no need to write unitless in the exam. Okay, so in this notes we just put unitless for your reference. Okay, in the real world you don't need to write like this. Okay, unless it becomes funny. Okay, so if there's no unit, that means no unit. Okay, example 2.8. For an amplifier with an output signal voltage, VR is equal to 4 volt, and output noise voltage, okay, uh, Vn out, okay, Vn out is equal to 0.005, and input and output resistance is 50 ohm. So this is the R. Okay, so determine the signal to noise ratio. Okay, so signal to noise ratio, the signal power is Vs square over R, divide with the noise power Vn square over R. So R and R can be cancelled out. So therefore 4R, 4 square, 4 volt square divide with 0.05 square. So you're gonna get 640,000. Okay, 640,000. From here, you can calculate the in decibel. 10 log, okay, 10 log 640,000. So you get 58 decibel. Okay, so this is SNR. Okay, so you see that the beauty of decibel is that it can convert a high value, a big value, into a small value 58, which is easy for us to do the calculation. Okay, so if you have question, please ask. Otherwise, I will move to the next slide. Okay, kalau ada soalan boleh tanya anytime. Okay, feel free to interrupt me anytime. Okay, you are most welcome to ask questions. Okay, noise factor and noise figure. Guys, this is very important. Okay, this is very important, and for sure it will come out in the test and final exam. Okay, so noise factor is equal to F. Okay, F equal to input signal to noise ratio divide with the output signal to noise ratio. What is this actually? So you see that class, if I draw again the previous picture, if we have a system like this, we have the input, we have the output. Okay, we have the input, we have the output. The input consists of signal input, and we also have the noise input. Then we have the output signal as out, and also and out. Okay, so in this case, that means we have SNR input. If I make a different color, okay, so that means we have SNR input, okay, at the input side, and we also have the SNR at the output side. SNRO. Okay, so noise factor is actually the SNRI. Okay, so this is actually SNR input divide with SNR output. Okay, so it is a ratio. And another parameter is noise figure and F. So it is actually 10 log, okay, 10 log of F. Okay, 10 log F, you're gonna get noise figure. Okay, so again, this is SNRI, and this is SNR output. Okay, so 10 log of noise factor in dB. So this is in dB. Okay, so you see that plus ideally, okay, ideally we want the value of F to be as minimum as possible. Ideally, the lower the value of F, the better will be the system. Okay, the better will be the quality of the transmitted signal. Ideally, we want F to be as minimum as possible. So if F is minimum, that means noise figure also would be minimum. Okay. Ideally, we want both parameters to be as minimum as possible. Okay. Ideally, we don't want both of these parameters to be high. Okay. We want both of these to be lower, the lowest possible. And if you see from here, the perfect noiseless circuit, for a perfect system without a noise, okay, F would be equal to 1. The minimum number of F would be 1. Okay, that means there's no, that means there's no difference in terms of SNR. Okay, we want the noise factor to be equal to 1. So this is the minimum values of F, minimum value of F. So if you see from here, 10 log of 1, okay, you're gonna get 0 dB. Okay, so this is the noise figure. So this is ideal, okay, which is not happen in the real world. So ideal system, we want our system to be closer to the ideal system. Okay, but this is not happen in the real world. Okay, so okay, for this picture, for these equations, we have to refer to this picture. Okay, so let's go through this picture. So there are two pictures here. Picture A is a ideal noiseless device, a device without a noise. And then the second picture is a device with a noise. Okay, a non-ideal device. So I can divide this into two parts. So you see that we have, if you picture A, class, picture A, we have an ideal noiseless amplifier over here, and it has a gain of AP. So it has a signal power SI and noise power NI. Okay, so you see that this is the symbol like this. So it has a AP equal to something. Okay, so the output, okay, S output is equal to APSI. Okay, APSI. Okay, and N output is equal to AP and I. Okay, so if you divide SO and NO, okay, you're gonna get APSI divide with APNI. So these can be cancelled out, and you're gonna get SI over NI, which is equal to the input. Okay. So in this case, you're gonna see that SNR input is equal to SNR output. So therefore, F equal to 1 and F equal to 0 dB. Okay, 10 log of 1, you're going to get 0 dB. Okay, so uh, okay, so this is for the ideal case. For a non-ideal case, for a non-ideal case, picture B. Okay, so you have a signal power as I, input power and I. So therefore, uh, if you you see that for a non-ideal case, we have the AP over here, the gain, and also the ND, internally generated noise by the system. Okay, so if I draw a symbol like this, okay, so this amplifier has a gain AP, and also it has an internally generated noise ND. Okay, so the output signal power SO is actually equal to the gain multiplied with the input, while the output noise, it is equivalent to the gain multiplied with the input noise, and you have to plus with the internally generated noise ND. Okay, and therefore for this case, you're going to see that SNR input is larger than SNR output. So that's why you're going to get F more than 1. Okay, and therefore the value of NF also larger than 0 dB. Okay, and you're going to see this later after this in the example. Okay, this one, Friis formula. So this is very important, class. This is very important. For sure, it will come out in the test and final exam. Okay, remember this will come out in the test and final exam. So Friis formula is used to calculate the noise factor for a cascaded amplifier system. Okay, so cascaded amplifiers are the amplifiers that connected in series like this. Okay, so when you have amplifier connected in series like this, you can calculate the total noise factor using the Friis formula. Okay, so you see that each amplifier has a gain and has a noise figure. Okay, amplifier 2 also has gain and noise figure. Amplifier 3 has gain and noise figure. Okay, so this is actually until N amplifier. Okay, so the Friis equation F total is equal to the noise factor from the first amplifier plus the noise factor from the second amplifier minus 1 divide with the gain from the first amplifier. So maybe I can make a simple drawing like this. Wait, so it is actually like this. So you have amplifier 1 connected to amplifier 2 connected to amplifier 3 like this. Each amplifier has a gain A1, this is A2, This is A3. Okay. And each amplifier has a value. Here is F1. So we also have F1 over here. Here is F2 over here. We also have the F3. Okay. So if you see from the Friis equations, the total F, let's say that we have until 3, for example. So maybe I can do 3. Okay, and then until n number. Okay, n number we have an and also fn. Okay, so Friis equation allow us to calculate until n number of amplifiers cascaded together. Okay, so if you see from the Friis equation, F1, okay, F1 is the noise factor of the first amplifier plus noise factor of the second amplifier minus 1 divide with gain from the first amplifier. Then plus with the noise factor of the third amplifier minus 1 divide with the total gain from the previous amplifiers. Okay, the gain from the first amplifier multiplied with the gain of the second amplifier. Okay, and then plus again until until noise factor of n amplifier minus 1 divide with the total gain of the previous amplifier A1 multiplied with A2 multiplied A3 until an minus 1. Okay, so you get a value of f total. F is a unitless parameter. Okay, so this is the noise, total noise factor. Okay, and if you see from here the total noise ft, okay, and you see that the notification remarks, okay, change unit of all noise factors f and power gains a from dB to unitless before you insert into the Friis formula equations. Class, this is very important. This is the common mistake by the students. Okay, if you see from here, all the values, okay, class, remember, all the values inside the Friis equation must be a unitless parameter. Do not put the decibel value inside the Friis equations. Okay, that means the f values and also the a values must be unitless. Okay, if you are given in terms of decibel, okay, if the question gives you in terms of decibel, you have to convert into a unitless parameter using anti-log. Okay, after you get a unitless parameter of f and also the a parameters, then you can use the Friis equation. Okay, be careful, class. I saw many times the student did careless mistakes by inserting decibel value inside the Friis equation. If you put decibel values, okay, if you put decibel values in any of these parameters, your answer would be wrong. Okay, remember f and also a parameter must be unitless when you use the Friis equation. Okay. Okay, so let's try to do the example 2.9. Class, I will not make a, I will not take a break. Okay, I will not take a break. If you want to take a break, you can take a break on your own. Okay, and I will continue until 11 o'clock. Okay, and make sure that you are here in the class 15 minutes before the end of class session. 15 minutes before 11 o'clock, I will give you the attendance. Okay, the attendance will be recorded 15 minutes before the 11 a.m. Okay. So example 2.9, if you read the example, the input signal to a telecommunications receiver consists of 100 microwatt of signal power and 1 microwatt of noise power. Okay, the receiver contributes to an additional 80 microwatt of noise and D, which has a power gain of 20 dB. Compute the SNR, the output SNR, and receiver noise figure. So what is this actually? So you have a receiver, okay? So receiver receives signal from outside. So you have a receiver like this. This is a receiver system, okay? So the input signal consists of, okay, so that means here SI, here is NI, okay? And you have a ND over here, okay? So SI, the input is 100 microwatt, input noise is 1 micro, and the receiver contributes additional 80 microwatt. And it has a gain. So the gain A is equal to 20 dB. Okay. So the question is, how much would be the SNRI? How much? And then SNRO, how much? And how much would be the noise figure and F? Okay. So we also don't know how much is SO. We don't know this. And out, also we don't know how much is this. Okay. So we have to calculate one by one. SNRI, SNRO, and noise figure. How much? Okay. So the first question asks you to find the SNR input. The first question. Okay. SNR input is equal to SI divided with NI. Okay. Input signal power divided with input noise power. So 100 microwatt. So this is given in the question. 100 microwatt divided with 1 microwatt. So you get 100. Okay. And then input SNR in decibel. Okay, when you want to calculate in terms of decibel, so 10 log of SNRI. Okay, 10 log 100, so you get 20 decibel. Okay, finish the first question. For the second question, you have to find out how much would be the SNR at the output. How much? Okay, so in order to calculate the SNR out, you have to find the S out and also the N out. How much? Okay, so I would like to calculate the S out first. Okay, so S out would be the power gain multiplied with the input signal power. Okay, so if you see from the question, you are given AP equal to 20 dB. Okay, so that means this is anti-log of 2. Okay, so you're gonna get 100. How do I get this? Okay, again, class 10 log of power. Okay, you're gonna get 20. Okay, So log of P is equal to 2. So P is equal to 10 power of 2. So you're going to get 100. Okay. So this is revision from chapter 1. Okay. So you see that the gain multiplied 100 multiplied with 100 microwatt. So I get 1 times 10 power of 2 watt, okay, of output signal power. Then I can calculate the N out. Okay, so N out is equal to internally generated noise ND plus power gain multiplied with input noise power. Okay, so the internally generated noise by the receiver plus 100 gain multiplied with 1 microwatt of input noise. So I get 1.8 times 10 power of 4 watt. Okay, so therefore SNR output, okay, SNRO is equal to output signal power, okay, output signal power divide with output noise power. Okay, so I get 55.56. Okay, and in terms of decibel, I can write 10 log of SNRO 55.56. So I get 17.45 dB. Okay, 17.45 dB. Okay, finish. The last question asks you to find how much would be the NF. Okay, how much would be the NF? In order to find the NF, we have to find the noise factor first. So how much would be the noise factor? Noise factor would be 10 log of, okay, so noise factor is actually what? Noise factor is actually SNR. Input divide with SNR output. Remember, the value that you put here should be unitless. Okay, so therefore input SNR, okay, input SNR is 100 from the previous question. 100, this one 100, okay, and output SNR is 55.56. Okay, so 100 divide with 55.56. Okay, and then 10 log of F, okay, 100 divide with 55.56, and then 10 log of answer, you're gonna get 2.55 dB. Okay, 2.55 dB. Straightforward, right? Class, can I get your response? Are you still there? Can you see my explanation here? Can I get your response?
Yes, Doctor.
Yes, doctor.
Okay. So if you have question about this, please ask question. Otherwise, I assume that you understand this. So if there's no questions, then I will move to the next example. Okay, example 2.10. Okay, so there are a lot of examples that you can try. Example 2.10, for a non-ideal amplifier and the following parameters. Okay, you are given the following parameters. Input signal power, you are given as I, and then so this is 2 power 10 of power of minus 10 watt. Input noise power, you are given an I, 2 times 10 power of minus 18. You are given a power gain A, 1 million, and you are given the internal noise value ND, 6 times 10 power of minus 12. Okay. So the first question asks you to find how much would be the input SNR in dB, then output SNR in dB, and then the noise factor and noise figure. So this is F and also NF. So this is similar with the previous question, similar with previous question. Okay, so input SNR is actually equal to SI over NI. Okay, SI over NI. 2 times 10 power of minus 10 divide with 2 times 10 power of minus 18. So you're going to get 1 times 10 power of 8. Okay, 1 times 10 power of 8. So from here, you can calculate the SNR in decibel. So 10 log of 100 million. So this is actually 100 millions. Okay, 100 millions. 10 log of 100 million, you're going to get 80 dB. So you see that the beauty of decibel is that it can reduce a big number into a small number, okay, which is good. And then what? The second question asks you to find the SNR output. Okay, in order to calculate SNR output, I would like to calculate S out first. Okay, S out is equal to gain multiplied with input signal power. So 1 million, okay, 1 million for the gain multiplied with the input signal power, 10 times 10 power of minus 10. So I get 2 times 10 power of minus 4. Then I calculate the N output. Output noise power is equal to internally generated noise plus, okay, gain multiplied with input signal, input noise power. So therefore 6 times 10 power of minus 12 plus the gain multiplied with the input noise. So we're going to get 8 times 10 power of minus 12 watt. Okay, so we get output noise power. We also have input noise power. Okay, so therefore the SNR out in decibel, so it becomes 10 log, okay, 10 log of S out divide with N out. Okay, and you're gonna get 74 dB. Finish. Okay, so how much is this actually? So if you see from here, 2 power of minus 4, yeah, 2 power of minus 4 divide with 8 power of minus 12. So this is actually 20, this is actually 25 million. Okay, 25 million. Okay. So you get 74 dB. Okay. 10 log. So 10 log answer 74. So it's actually 73.979. So 74. Okay. And then what? So next, find the noise factor. Noise factor is equal to SNRI, SNR input, divide with SNR output. Okay, so this is 100 million divide with 25 million. So you get 4. Okay, so this is noise factor. So therefore, noise figure is equal to 10 log of noise factor. So you're going to get 6.02 decibel. Okay, very easy, right? So this one is easy example. Okay, straightforward. So if you have question, please ask. Otherwise, I will move to the next slide. Okay, so feel free to ask me questions. So I like students to ask questions. Okay, So don't be passive. If you don't understand, you can ask. Okay, if you need further explanation, I will try to give further explanation to you. Okay. Again, next example. Okay, the next example, for a three cascaded amplifier stages, each with noise figure 3 dB and power gains of 10 dB. Determine the total noise figure. So what does it mean? So class, when you get this kind of question, okay, my suggestion would be to draw. Okay, it is better for you to draw. So you have three cascaded amplifiers. Okay, so you have the first amplifier, okay, and then you have the second amplifier, then you have the third amplifier. Each amplifier has a noise figure of 3 dB, okay, each of it. So NF1 3 dB, NF2 3 dB, and also NF3 also 3 dB. And then what? Power gain 10 dB. So A1 is equal to 10 dB. A2 also 10 dB. A3 also equal to 10 dB. Okay. So the question asks you to find how much would be the NF total. In order to find this, first you have to find how much would be the F total using the Friis equation. From F total, then you can find the NF total. Okay. So if you see from here, all the power gain is equal to 10 dB. Okay. So A1 equal to A2 equal to A3. So if you want to convert 10 dB into a unitless parameter, okay, so anti-log of 1, you're going to get 10. Okay, so I repeat again, 10 log of a value, 10 log of A is equal to 10 dB. A is equal to 10, like this. Okay. Similar with noise figure. Okay. So you are given the same noise figure NF1 and F2 and F3. That means F1 equal to F2 equal to F3. So F is actually anti-log of noise figure. Okay, so you see that class 10 log of F is equal to 3 dB. Okay, so therefore F is actually 10 power of 0.3. Okay, 10 power anti-log of 0.3. Okay, anti-log of 0.3, you're gonna get 1.995. Okay, 1.995. Okay, so in the exam, I would suggest you to write up to minimum 3 decimal point. Okay, my suggestion. In the lecture notes, they just put 2 for easy calculation, for easy reference for you. Okay, but in the real exam, you have to write up to 3 decimal point at least. Okay, that's my suggestion. Okay, but for example, no problem. Okay, for these examples, no problem. If you do like this in the real exam, there's gonna be a problem. Okay, in the real exam, in the real test, don't write fixed number. Okay, you have to write the decimal point as well. Okay, so So now we know the A value and we also know the F value. Then we can find the total noise factor, F total. Okay. So the F total, would be F1 plus F2 minus 1 divide with the gain from the first amplifier plus the noise factor of the third amplifier minus 1 divide with the total gain from the previous amplifier A1 multiplied with A2. Okay, so in the exam, we normally ask you up to 3 cascaded amplifiers. Okay, you don't need to learn up to 4, 5, 6 amplifiers. 3 amplifiers is enough. Okay, so if you put the value 2 plus 2 minus 1 over 10, okay, I make a bracket. And then 2 minus 1 over 10 times 10. So I get 2.11. Okay, 2.11. So therefore, the total noise figure is equal to 10 log of 2.11. So this is actually 10 log of F total. So you're going to get 3.24 dB. Finish. Okay, finish. Straightforward, right? So it's easy. So if you have question, please ask. Otherwise, we're gonna learn the next slide. Okay, kalau ada soalan, sila tanya. Otherwise, I will move to the next slide. Okay. Equivalent noise temperature. What is this? Equivalent noise temperature. So if you see from here, TE, TE is the equivalent noise temperature. In order to calculate TE, so we can refer to the T parameter. Remember that Pn is equal to KTB, right? So the ambient temperature T is equal to Pn divided with K Boltzmann constant multiplied with the bandwidth, okay, which is referred to this equations. So don't be confused. In your lecture notes, this is the noise power. N is a noise power. So in your lecture notes, if you see that sometimes it is referred as N, sometimes it is referred as Pn. So both are the same. So don't worry. Okay. And from these equations, actually we can write the TE equations. Okay. So TE is a hypothetical value that cannot be directly measured. Okay. So you see that the lower the TE, the better will be the quality of the receiver. Okay. So ideally, we want the TE parameter to be as low as possible. The lower the value will be better. Okay. So TE is equal to T times F minus 1. Okay. The equivalent noise temperature equal to ambient temperature multiplied with noise factor minus 1. Ambient temperature by default in your lecture notes is 290 Kelvin, which is equal to 17 degrees Celsius. But this depends on the questions, okay? In the exam, in the final exam or in the test, we will provide the ambient temperature, okay? And if you rearrange the equations, okay, you're gonna get F equal to 1 plus TE minus TE over T, okay? 1 plus TE over T. Okay, so So you can rearrange the equation to become like this. Okay. So example 2.12, if you see from here, example 2.12, determine the noise figure. Okay. Determine the NF for an equivalent noise temperature. Okay. Equivalent noise temperature, TE, equal to 75 K. Okay. So in order to determine an F, you need to find F. Okay. F, as we have seen before, is equal to 1 plus TE over T. Okay. And by default, the ambient temperature in your lecture notes is 290 Kelvin by default. Okay. So you can calculate the noise factor 1 plus TE over T, which is equal to 1 plus 75 Kelvin divided with ambient temperature 290 Kelvin. So you're going to get 1.258, 1.258, no unit. Okay. And then you can convert into noise figure. So 10 log of F, okay, you're going to get 1 dB. Okay. So if you see 10 log 1.258, you're going to get 0.9968. So this is actually 0.996868, okay, dB. So equivalent to 1 dB. Okay, equivalent to 1 dB. Then the second question asks you to find the equivalent noise temperature. So you have to find TE if you are given noise figure and F equal to 6 dB. Okay, so therefore we can find the noise factor. Noise factor is the antilog of noise figure. Okay, antilog of 0.6. Okay, antilog of 0.6. Okay, because it is like this, right? 10 log F is equal to 6 dB. So F is antilog of 0.6. So you're going to get 4. Okay. So if you use a calculator, antilog of 0.6, you're going to get 3.98. So this is actually 3.9811. Okay. So it has been rounded up to 4 in this lecture notes. Okay. So once you get the F value, then you can put inside the equations. TE equal to ambient temperature multiplied with noise factor minus 1. So 290 Kelvin by default room temperature multiplied with 4 minus 1. So you get 870 Kelvin. Okay, very easy, straightforward. Okay. So if you have question, please ask. Otherwise, we can see the other examples. Okay. Noise measurement. So this is when you measure the. This is when you measure the noise. Okay. So you have a device that you can measure the noise voltage. Okay. At a certain distance, you can measure the noise voltage at a certain distance. Okay, this is when you do the measurement. Okay, you transmit signal and you can find the noise value at a certain distance. And if you see from here, so this is when we take the noise measurement. Sorry, when we do the noise measurement to measure the amount of noise at different time. Okay, so in this example, we measure a noise voltage at different time and we get a few values, a few set of values. Okay, So if you see from here, assuming that we take a measurement 10 times at different time, okay, so I have a system transmitted system. The system transmitter transmit a signal, and I want to measure how much would be the noise value, okay, at 10 different time. And I get the value when I measure using the voltmeter. I get the value 0.3, sorry, minus 0.3 volt, 1.0 volt, 0.2 volt, 0.5 volt, until 0.9 volt. Okay, so I measured 10 times at different time. I get 10 different values. Okay, so these are the noise voltage values measured using the voltmeter, okay, in this example. So now the issue is we want to find the RMS noise voltage. Okay, we want to find the RMS noise voltage. In order to do that, there are a few steps. Okay, the first step is to find the sum of the square values. Okay, sum of quadratic values. So therefore, I have to find the summation of quadratic values, v1 square plus v2 square plus v3 square plus v4 square plus v6 square, v7, v8, v9, and 1, 2, 3, 4, 5. Sorry. And so this is 1, 2, 3, 4, 5, v6, v7, v8, v9, and v10 square. Okay, so we add all the quadratic summations, okay, and we get 3.0325 volt square. Okay, 3.0325 volt square. So this is if we have 10 readings. If we have 100 readings, 100 measurements, then we have to make a quadratic summation up to 100 values. Okay, so in this example, only 10. Okay, so therefore, we finish the first step. The second step is to find the average quadratic summation. So the average square summation, average quadratic summations is 3.0325. So this is a volt square divide with 10. Why we divide with 10? Because we have 10 values. Okay, we have 10 values. If we have 100 values, then we have to divide with 100. Okay, so the average is, that means we divide with the total number of values. How many values we have? Okay, so therefore 0.30325 volt square. Okay, then the final step, okay, the final step is to find the root mean square, which is square root of the average value. Okay, square root of the average value, so we get 0.55 volt. Okay, 0.55 volt. Okay, so finish. Okay, so this is the RMS noise voltage. So this is the RMS noise voltage. Okay, then example 2.13. Okay, example 2.13, also similar. Okay, also similar. Okay, similar like the previous question, similar like the previous example. So you also measure the noise voltage using the voltmeter, okay, at 10 different times. So you get 10 values. Okay, you get 10 values, 10 minus 100 millivolt, 35 millivolt, minus 57, until you get minus 20. So this is V1, V2, V3, V4, V5, V6, V7, V8, V9, V10. Okay. So in order to find the RMS noise voltage, the first step, okay, the first step is to find the quadratic summation, okay, the square summations, okay, the quadratic summations. So V1 square plus V2 square, okay, so this is V1 square, V2 square, V3 square, 4 square, V5 square, V6 square, V7, V8 square, V9, V10 square. Okay, so you get 24,751 millivolts square. The second step would be to find the average value. Okay, we divide with 10 because we have 10 readings. So that's why we divide with 10. So therefore we get 2471.1, 2475.1 millivolts square. Okay. Then the final step would be to find the RMS noise voltage. That means it is a square root of 2475.1 millivolt square. So you get 49.75 millivolt. Okay. Finish. Chapter 2, finish. Okay. But I want to show you another example. I want to show you another example. Class, can you see my screen? Can I get your response?
Boleh, Doktor.
Okay. Yeah. I have another example that I want to show you. Wait, I will find the example. Um, Okay, I will share my screen again. Okay. Okay, can you see my screen?
Yes, doctor.
Okay, thank you. So let's do the example from previous test questions. So this is a long time ago, 2014. 2014. If you see, this is not this semester. Okay. Sometimes I afraid that I accidentally shows the current semester. Okay. So
Doktor,
this
sorry.
is, yeah. Sorry, yeah.
Saya ada tukar account sebab account ni saya tak berapa nak clear. Boleh
Apa
doktor
apa ya?
tengok tak? Accept. Tu, Azim Haikal
Oh,
doktor.
okay, okay.
Terima kasih doktor.
Okay, sama. Okay. Okay, you can see my screen, right? Can I get your response? Boleh nampak,
Can doktor, can.
Nampak,
Okay.
doktor.
Okay. So this is a long time ago, 2014, October 2014. So you see that this is the previous questions. Question 1, and then question number 2. So this is the question that I want to show you. Question number 2. Okay. So the first question is about intermodulation distortion. So this is, I think you can get the answer from the lecture notes. Okay. Intermodulation distortion is a mixing of two or more input signal that has been amplified in a nonlinear device, which produce a sum and difference frequency, the cross product. And then you can draw the picture. So in this kind of example, you have to explain and you have to provide a suitable diagram. Okay. So the suitable diagram, you see that we have the two input. Okay, when you put inside a nonlinear device, it will produce a sum and difference frequencies. Okay, so we have the V fundamental two input. Okay, so this is the V difference, and this is a V sum. Okay, so this is F1, F2. So we have F1 minus F2, F1 minus plus F2. Okay. So this is F1, F2. Okay, so this is about the intermodulation distortion. And the thing I want to show you is about the question 2B. Okay. So question 2B, if you see from here, okay, question 2B, an analog receiver system consists of an antenna and 3 cascaded RF amplifiers shows in the system 2B. So you see that you are given the environment temperature 17 degrees Celsius. So 17 degrees Celsius, if you convert 17 plus 293, so you're going to get 290 Kelvin. Okay. So you are also given the signal transmission bandwidth 300 megahertz. So this is the B parameter. Okay. And if you see from here, from the picture, this is the receiver system. So this receiver system, if you see from here, you are given the input signal power SI as 5 watt. And you are not given the input noise. We don't know how much. Okay. And this receiver consists of 3 different amplifiers. Okay. Each amplifier is given the A1 parameter, the gain parameter 4 dB, and then A2 5 dB, A3 20. Okay, so you might wonder about this. This is 20, not 20 dB. Okay, sometimes we like to test the students. This is 20, not 20 dB. Okay. And then TE1 is 77 degrees Celsius. You see that we give you Celsius. And then here is 300 Kelvin and 450 Kelvin. And if you see from here, the S out is not given. We don't know how much S out. We don't know how much is N out. Okay. And determine the input signal to noise ratio in decibel. Okay, SNR, I in dB. Okay, in decibel. How much? Okay. So how to do this? Okay, so let me answer this. So SNR I is equal to SI divided with NI. Okay, so SI we know, NI we don't know. How to calculate NI? Okay, how to calculate NI? So if you see from here, class, we actually can calculate the input noise by using the what? Using the KTB. KTB. Okay. So KTB is equal to 1.38 times 10 power of minus 23. Okay. Times 290 times B is 300 mega times 300 mega 10 power of 6. Okay, so this is 1.38. So you're gonna get 1.2 picowatt. Okay, 1.2 picowatt. Okay, so from here we can calculate the SNRI. SNRI is equal to SI over NI. So this is SI is given in the question 5 watt divide with 1.2 picowatt. So you're gonna get 4.167 times 10 power of 12. Okay. And if you want to find it in terms of decibel, okay, if you want to find it in terms of decibel, that means we can calculate like this. So this is 10 log 4.167 times 10 power of 12. Okay, so we get this is 126.198 dB. Okay, finish the first question. Okay, and then what? The second question, calculate the total noise factor, F total. How much would be the F total? In order to do this, you have to find out how much would be the F1, F2, F3. Okay, you have to find out how much would be the F1, how much would be F2, and how much would be F3 first. Okay, in order to do that, okay, you can use the equivalent noise temperature equation. Okay, so therefore F1 is equal to 1 plus TE1 over ambient temperature. So this is 1 plus 350 Kelvin divided with 290 Kelvin. How do I know 350? Okay, 77 degree. If you see 77 plus 273, so you get this one is 350 Kelvin. Okay, remember all degrees Celsius must be changed into Kelvin. Okay, so this is I get this 2.201. Okay, plus please correct me if I'm wrong. Please correct me if I'm wrong. Okay, F2 is equal to 1 plus TE2 divided with the ambient temperature. So this is 1 plus 300 from the question, divide with ambient temperature. So I get this 2.034. Okay. And F3 is equal to 1 plus TE3 divided with ambient temperature. So this is 1 plus 450 divided with ambient temperature. And then I get this 2.552. Okay. So class, please help me to calculate as well. Okay. So that we can cross-check each other. Okay. So from here, I can calculate the F total, which is using the freeze equation. F1 plus F2 minus 1 divide with A1 plus F3 minus 1 divide with the total gain of the previous amplifiers. Okay, so I get this around 2.808. You can try this, okay, class, you can try this. A1, okay, A1, how much is A1? So A1, so you have to change all the values of A. So A1 is equal to anti-log of 0.4. So you're going to get 2.51. Okay, 119. A2 is equal to anti-log of 0.5. So this is 3.1623. Okay. If you do the anti-log. Okay. So let's try 2.201. Okay, plus 2.034 minus 1. So 1.034 divided with A1. How much A1? 2.5119 plus 1.552 divide with this one, 2.5119 times 3.1623. So I get 2.808. Okay. Finish. Okay, finish. And then find the output signal power SO in watt and output noise power NO in dBW. So how to do this? How to do this? So class, if I'm wrong, please correct me. Okay. In order to find the SO, what we can do is we need to find the total A first, the total A. So A total is equal to A1 multiplied with A2 multiplied with A3. Okay, so this is equal to anti-log of 0.4 multiplied with anti-log 0.5 multiplied with 20. So I get this 158.866. Okay, so please correct me if I'm wrong. Okay, so therefore the S out, okay, output signal power is actually the A total multiplied with the SI, input signal power. So this is 158.866 multiplied with input signal power 5 watt. Okay, so I'm gonna get this around 794.328 watt. Okay, 798.328 watt. Okay, and then what? From here, what I can do is that I can find the N out. Okay, I can find the N out. Okay, so how to find the N out? In order to find the N out, first I can find the SNRO. How much would be the SNRO? So this is SO. So this is SO. So if you see from here, SNRO is actually equal to, you see that from the F total, we know that this is SNRI divided with SNRO. Okay, so SNRO is actually equal to SNRI divided with F total. Divide with F total. So what I can find here is that SNRO, okay, SNRO is actually equal to 4.167 times 10 power of 12. How do I get this from the first question? From the first question, we already find the first SNR input. Okay, from the first question. Okay, from the first question, 4.167 times 10 power of 12 divide with the total noise factor that we already calculate, 2.808 divide with 2.808. Okay, so how much is this? Okay, 4.167 exponent 12 divide with 2.808. So I get this 1.484 times 10 power of 12. Okay. Class, please correct me if I'm wrong. Please correct me if I'm wrong. Okay. So this is SNRO. So therefore, when we want to calculate NO, okay, NO is actually equal to SO divided with SNRO. Okay, so therefore we can write like this. SO is 794.328 watt divide with SNRO that we have just calculated. This one, 1.484 times 10 power of 12. Okay, so how much is this? Okay, so 794.328, okay, divide with 1.484 exponent 12. Okay, so I get 5.3526 times 10 power of 10 watt. Okay, please correct me if I'm wrong. Okay, so therefore in dBW and out in dBW, this is 10 log 5.346 times 10 power of 10. Okay, so I get this, how much? Class, let's calculate together. 10 log 5.3526 exponent 10. Okay, so this is, sorry. Kenapa tak ada yang betulkan saya? Kelas, kat mana salah dia? 794.328 divide with yang atas sudah salah 1.484 exponent 12. So it's actually minus 10. This one is minus 10. Okay, minus 10. So 10 log 5.3526 exponent minus 10. So I get minus 92 minus 92.714 dBW. Okay, 714 dBW. Okay. Can I get your response? Are you still there?
Yes, doctor.
Okay.
Doctor.
So this is it, in dBW. And then what? The last question, last question mentioned that the receiver output signal to noise ratio can be improved by using a suitable configuration for a cascaded RF amplifier system. In your opinion, which RF amplifier should be placed at the first stage and why? What is this actually? So plus, if you see from the Friis equation, we want the F total, okay, we want the F total to be as minimum as possible. Remember, okay, in order to do that, we can improve the system by rearranging the amplifier. Okay, rearrange means that which amplifier should be placed at the first stage, second stage, and the third stage. Which one? Okay, so in order to answer that, okay, we need to choose an amplifier with the least noise factor to be the first stage. Okay, that means you see that the amplifier with the least noise factor is amplifier 2, followed by first amplifier, and then the last amplifier. So when I want to rearrange, okay, I will put the second amplifier first, okay, and then I put the first amplifier, and then the third amplifier. So this is how I arrange this, okay, and I will put an amplifier with the least noise factor as the first stage. Okay. So therefore, I will get the F total less than 2.808. Okay. You can try to prove it later. Okay. You can try to prove it later. Okay. The key point here is that amplifier with the least noise factor should be at the first stage, followed by the amplifier with the second lower noise factor, and the last one would be the amplifier with the highest noise factor. So this is how you rearrange the amplifier to produce the least value, the minimum value of noise factor, total noise factor. Okay. And don't worry, I will share this later after this. Okay, I will share this in the group later. Okay. So class, we can take the attendance. So sorry, I take 6 minutes more than the 11 o'clock. So don't worry, I will share this later. So you see that class, this kind of question is final exam style question. Okay, so you have to get used to play around with the multiplication, decibel calculation, and so on. Okay. So you can open your QR code reader, okay, and you can take the attendance, and you can go anywhere you like after this, okay? Class, are you still there?
Yes, Doktor.
Okay. Sorry lah selalu tanya ni sebab otherwise student hilang nanti So I will open the QR code. You can scan the attendance, okay? So see you again next week on Tuesday. So next week will be physical classroom session. Okay? Boleh scan tak?
Boleh ada.
Okay. Semua dah scan ya? Kenapa dia punya jumlah tak berkurang? Is there any technical issue?
Doktor, saya tak boleh nak scan, Doktor. Saya ada masalah kamera.
Semua tak boleh scan Anybody can scan the attendance?
Scan ada.
Cannot scan?
Boleh.
Boleh?
Boleh. Dia tak link.
Tak boleh scan? Siapa yang tak boleh scan? Ya. One by one nanti kejap. Don't worry. Siapa boleh scan dulu. Try to scan first. Later yang tak boleh scan nanti boleh you can inform me after this I will tick manually. Dia macam slow sikit Siapa lagi? Saya tick semua attend lah senang. Okay, ni macam dah boleh sikit ni. Sekejap Okay, siapa yang belum take attendance? Siapa nama? Slow lah.
Saya, Doktor.
Inilah masalah ni lah sistem TCIS ni. Sistem attendance ni dia. Okay, never mind. I will assume that all of you attend the class. Okay? Simple. Okay, all of you, I assume attend the class, so it's okay. So I think that's all for today, class. That's all for today. And I assume that all of you attend the class, okay? So there's a connection error, internet error. Okay, so that's all, class. All of you attend the class, so no need to take the attendance. I assume all of you attend the class, okay? So that's all for today. Goodbye. See you again next week.
Thank you, Doctor.
See you again next week on Tuesday in the physical classroom. Okay. Hopefully all of you can attend the class next week. Okay. See you again. Selamat Hari Raya. Okay. Eid Mubarak to all of you.
Thank you, Doktor.
Okay. Bye.
Thank you, Doktor.
Doktor, selamat hari raya.
Welcome.